I want you to try a little thought experiment with me to start things off today.
Okay, I'm ready.
Picture yourself standing in the middle of a vast, just sweeping desert. Miles and miles of rolling sand dunes, completely baking in the sun.
Sounds pretty bleak, honestly.
Right. But here's the catch. Hidden in that sand, scattered totally at random, is gold dust.
Oh, okay. That changes things.
Exactly. Billions of dollars worth of pure gold, but it is just mixed right into the dirt, grain for grain. Now, if you wanted that gold, the traditional human approach is, well, it's incredibly brutal.
Yeah, we'd essentially bring in fleets of massive diesel excavators.
Right. We'd shovel up millions of tons of that sand, dump it into these toxic chemical baths, sift it, process it, and basically leave behind this scarred, completely devastated landscape. And all of that just to get a few handfuls of metal.
It's remarkably inefficient, yeah.
It really is. But what if you didn't have to move a single grain of sand? What if instead you could just stand there and, I don't know, hum a very specific, perfectly tuned frequency? Yeah. And in response to that song, only the gold began to vibrate, levitate, and literally fly right out of the dunes into your hands, leaving the desert completely untouched.
I mean, it sounds like a scene out of a high fantasy novel, right? Literal magic.
It sounds like telekinesis.
Yeah.
But what's absolutely wild about the material we are diving into today is that we are not talking about magic.
No, we are definitely not.
We're talking about hard physics, incredibly advanced microelectronics, and a very real, very imminent technological leap. Welcome to the deep dive, everyone. We have gotten our hands on a truly fascinating stack of documents today.
Yeah, we've got a highly restricted strategic notification brief alongside this deeply technical concept paper from a group called the Astra-Arctic AI Expedition.
Right, or AAE, authored by a deep tech researcher operating out of Tallinn, Estonia, named Alexander Kriminov.
And look, the concepts embedded in these documents are dense. We are not looking at some consumer gadget here.
Not at all.
We're looking at classified level engineering, complex international patent strategies, and really a fundamental ground-up rethinking of how machines actually interact with the physical world.
So the core of this deep dive revolves around a technology called I-DPCM, which stands for Intellectually Defined Processing of Conductive Material.
It's a mouthful.
It is a mouthful. But the documents describe it as an intelligent electromagnetic cyber actuator. And the promise here is just staggering. It's this radically new category of robotic payload that could completely upend how humanity extracts critical resources from, say, the deepest parts of the ocean.
Or how we clean up the terrifying amount of debris currently orbiting our planet.
Yes. Or even how we might eventually mine asteroids in deep space.
Right. So our mission today is to break down this highly technical blueprint and translate it into a thrilling, accessible scientific narrative just for you. We're going to look at the hard physics, the electromagnetism, the material science, the semiconductors that actually make this possible.
And we really have to look at the massive geopolitical and ecological implications, too. Because if this technology scales the way the AAA documents suggest it can, it is going to touch almost every single aspect of our modern technosphere.
It really will.
Let's start with the big picture, though. Because before we can even begin to understand how this cyber actuator actually works, we need to intimately understand the current bottleneck in modern robotics.
Wait, the problem we're trying to solve.
Exactly. Because robots today are brilliant in some areas, but shockingly primitive in others.
Yeah.
Like they're incredibly good at seeing the world.
Oh, absolutely. We have LiDAR, 4K optical sensors, thermal imaging. I mean, you can send a drone over a forest, and it can map every single leaf down to the millimeter.
Yeah, the sensory input is flawless.
Yeah.
But the moment that robot has to actually reach out and touch the physical world,
it all goes wrong.
It really does. They become remarkably destructive.
It's a total crisis of physical interaction. We have spent, decades perfecting the sensory inputs for artificial intelligence. But the outputs, the actual physical hands, claws, and treads, are still based on the exact same mechanical principles we used during the Industrial Revolution.
Right. It's like we're slapping cutting-edge artificial intelligence onto a 19th century bulldozer.
That's a perfect way to put it. And in the cheap AE documents, the author highlights that this reliance on mechanical force is actually manifesting in 3 distinct, massive crises across our civilization right now.
Okay, let's break those down. The first one hits very close to home because it directly involves the devices you use every single day. The brief refers to it as the Critical Raw Materials Deficit.
Right, the CRMA. The European Union recently passed the Critical Raw Materials Act, and they have been raising massive red flags about this.
Because we have this desperate, insatiable need for specific elements, rare earths, gold, platinum, copper, neodymium, dysprosium.
You literally cannot build modern society without them. You need these for wind turbines, for the batteries in electric vehicles, for the semiconductor chips inside the smartphone in your pocket.
And the transition to green energy and a digital economy requires an exponential increase in these materials.
Exponential. But getting them out of the ground is a nightmare. Traditional terrestrial mining relies heavily on quarrying, dredging, and blasting.
Like the desert analogy we started with.
Exactly. You have to literally tear mountains apart. You move millions of tons of useless rock and soil to get a microscopic yield of the metal you actually want.
And we are running out of easy terrestrial mines. So where is the industry looking next? The deep sea.
The abyssal plain.
Right. The ocean floor, specifically in areas like the Clarion-Clipperton Zone in the Pacific, is absolutely littered with what are called polymetallic nodules.
They look like little black potatoes just sitting on the mud.
Yeah, little black potatoes that are incredibly rich in these rare metals. But if we try to harvest them using our current mechanical paradigm, the results are catastrophic.
Because if you send a traditional robotic mining machine down to the abyssal plain, it relies on treads to move and mechanical dredges to scoop. So it essentially bulldozes the seabed.
It just crushes everything.
It does. And when it does that, it sucks up the nodules, sure, but it also sucks up the mud, the sediment, and all the microscopic life living there. And this creates massive, highly destructive silt plumes.
Which is like a dust storm, but entirely underwater.
Right. Exactly. And these plumes can drift for hundreds of miles on deep ocean currents. As the silt settles, it essentially suffocates entire benthic ecosystems that have remained completely undisturbed for millions of years.
Which totally explains why regulatory bodies, like the International Seabed Authority, are heavily restricting or outright banning a lot of these proposed methods.
They have to. The ecological cost is just too high.
But there's a glaring irony here that I really couldn't stop thinking about while reading the brief. We absolutely need these specific metals to build our green energy infrastructure, literally to save the planetary environment from catastrophic climate change. Isn't it a massive paradox that the only way we currently know how to extract them physically destroys the environment in the process?
Oh, it is arguably the defining paradox of the entire green transition. We are trying to build a sustainable future using highly unsustainable brute mechanical force.
Right.
The physics of dragging a metal claw through ocean mud simply does not allow for a clean extraction. That is the first massive failure of mechanical interaction.
Okay, but the brief points out that this failure isn't just limited to the bottom of the ocean. If we look up, we see the exact same physical bottleneck causing a completely different crisis in space.
The Kessler syndrome.
Ugh. This is one of those concepts that genuinely gives me anxiety whenever I think about it.
It's terrifying.
It really is. Low Earth orbit is currently choked with debris. And we're not just talking about a few dead satellites. We were talking about millions of pieces of man-made metallic shrapnel.
Everything from old rocket boosters to tiny flecks of paint and loose bolts.
And they're all whipping around the planet at roughly 17,000 miles an hour.
Right. And at those hypervelocities, a piece of debris the size of a marble carries the kinetic energy of an anvil dropped from a skyscraper.
Oh, wow.
Yeah, it can instantly destroy a multi-billion-dollar communications satellite or, punch a hole right through the International Space Station. And the real issue is that the more things collide, the more debris they create, which leads to a cascading chain reaction.
That cascade is the Kessler syndrome.
Exactly.
So space agencies are desperately trying to figure out active debris removal, or ADR, but the current ideas all seem to rely on that same flawed mechanical paradigm we just talked about with ocean mining. I've seen proposals to send up robots with giant nets or harpoons or robotic arms to physically catch this debris.
It sounds incredible in a sci-fi movie.
Right, but practically speaking, is that even possible?
No. If you sit down and actually run the math on orbital mechanics, physical capture is economically and mathematically impossible on a planetary scale. Because in orbit, you don't just drive up next to something. To catch a piece of debris, your robot has to match its exact speed, its altitude, and its precise orbital trajectory.
Which requires fuel.
A lot of fuel. In orbital mechanics, we call this delta V, the change in velocity.
So if a cleanup robot catches one stray bolt, it has to burn a massive amount of its onboard fuel just to change its orbit and catch the next piece of debris.
Precisely. You would essentially need to launch a massive, heavily fueled robot into space for almost every single piece of debris you wanted to catch. The launch costs alone would bankrupt every space agency on Earth.
So you cannot rely on physical mechanical touching to solve a problem that is spread across the entire volume of low Earth orbit.
It is an insurmountable physics problem.
Okay, so we have dragging claws through ocean mud, and we have trying to catch hypervelocity bullets with a net. Let's look even further out to the third crisis outlined in the IKAE papers, space resource extraction, or what the industry calls in situ resource utilization. Right, we are entering a new space race. Nations and private companies want to build permanent bases on the Moon, on Mars, and eventually mine highly metallic near-Earth asteroids, like the asteroid Psyche.
And the logic there is totally sound. It is incredibly expensive to launch steel and fuel out of Earth's gravity well. So if we want a permanent presence in space, we have to mine the materials that are already up there.
But once again, Earth-based mechanics completely fail us.
Yeah.
When we try to dig in space, we run into two massive physical barriers.
Right.
The lack of gravity and the abrasive nature of the environment.
Let's talk about the gravity part first, because it's so intuitive once you think about it. If you put a heavy mechanical excavator on a small asteroid, it has almost zero weight.
Right.
So the moment it tries to push its shovel down into the rock, Newton's third law takes over. The equal and opposite reaction just pushes the excavator off the surface and sends it tumbling backward into space.
It has absolutely no traction.
None. It cannot generate the downward force required to break the rock. And even if you could somehow anchor the machine, you run into the second problem, the regolith.
The space dust.
Yes. Lunar and asteroid dust is not like dirt on Earth. Earth's dirt has been weathered by billions of years of wind and water. The particles are smooth and round. Space dust has never been weathered. It is essentially microscopic, jagged shards of glass.
And those shards get into everything, right?
They do. They get into mechanical gears, drill bits, pneumatic joints, and bearings. Because it is so sharp and abrasive, it shreds conventional mechanical systems almost instantly.
Wow.
I mean, during the Apollo missions, the lunar dust famously degraded the astronauts' spacesuits in a matter of days. So mechanical drilling in a vacuum is just a dead end.
Let's synthesize what we just laid out, because the through line here is incredible. We've got the ocean floor, low Earth orbit, and asteroid mining. On the surface, these seem like completely isolated challenges belonging to entirely different scientific fields: marine biology, aerospace engineering, and terrestrial mining.
But they're not.
Right. The AAE documents point out they all share the exact same physical bottleneck. The question is, how do you selectively interact with conductive objects, like rare metals, hidden inside a non-conductive medium, whether that medium is ocean water, the vacuum of space, or highly abrasive lunar dirt, without tearing that medium apart or destroying your robot in the process?
And the author of the brief, Krimenov, arrives at a very stark conclusion. You cannot solve this by building a better mechanical claw. You have to abandon mechanical force entirely.
You cannot physically touch the target.
Exactly. To interact with the physical world at this new scale, robotics has to transition from a mechanical paradigm to what physics calls a ponderomotive, or electromagnetic, paradigm.
And this is where we finally get into the hardware of I-DPCM, because the solution they're proposing isn't a shovel or a drill. The core physical unit is a linear inductor. It's essentially a highly specialized coil made of something called Lip's wire, which is then wrapped around a nanocrystalline core.
And every single material choice in this device is highly deliberate. It's engineered to solve very specific physics problems. Let's unpack the wire first.
Yeah, why Lip's wire?
Because if you try to push high-frequency alternating current through a standard, solid copper wire, you run into a phenomenon known as the skin effect.
Now, I've heard of the skin effect in relation to power lines, but what is actually happening inside the wire?
Well, when you push an alternating current, a current that rapidly changes direction, it creates its own oscillating magnetic field inside the wire. And that internal magnetic field actually pushes the electrons outward.
Outward toward the edges.
Exactly. So instead of flowing evenly through the entire cross-section of the wire, the electrical current gets crowded to the very outer edges, the skin of the wire.
Oh, I see. It's like if you have a massive wide hallway, but all the commuters suddenly press themselves against the walls to walk. The middle of the hallway is completely empty, but the edges are a cramped, chaotic mess.
That is an excellent way to visualize it. And because all those electrons are crammed into a tiny space at the edge, it creates massive electrical resistance. Higher resistance generates a tremendous amount of heat.
Which is bad.
Very bad. If you ran the kind of power I-DPCM requires through a standard wire, the skin effect would cause the coil to literally melt itself into a puddle of slag in seconds.
Okay, so how does Litzwire solve the commuter problem?
Litzwire gets around this by taking hundreds, sometimes thousands, of microscopic, individually insulated threads of copper and intricately weaving them together into a single, thicker cable. Yeah, by breaking one big wire into hundreds of tiny insulated wires, you drastically increase the total surface area. The current is forced to distribute evenly across all those tiny individual skins.
So it maximizes the flow, completely neutralizing the skid effect.
Exactly, and that allows ultra-high frequency currents to flow efficiently without generating that catastrophic heat.
Okay, so the intricate weaving of the Litzwire solves the heat problem from the electrical current. But what about the core it's wrapped around? The document mentions a nanocrystalline core. Isn't creating a massive magnetic pulse going to generate its own kind of stress?
Absolutely. The core is the backbone of the electromagnet. If you use a standard iron core, it simply cannot handle the extreme magnetic loads required here. It reaches what is called magnetic saturation too quickly.
What does that mean practically?
Think of a sponge soaking up water. Once the sponge is completely saturated, you can pour a gallon of water on it, but it won't absorb anymore, right? The water just runs off.
Right, it's maxed out.
A magnetic core is similar. It helps amplify and direct the magnetic field. But once it hits saturation, pouring more electrical power into the coil doesn't make the magnetic field any stronger. The excess energy just converts into wasted heat.
So the nanocrystalline core changes that limit.
Yes. A nanocrystalline core is a specialized material with a highly uniform microscopic crystal structure. It has an incredibly high saturation point. It allows the device to generate staggeringly powerful magnetic fields without tapping out.
Wow.
And crucially, it maintains that performance whether it is operating in the freezing, crushing depths of the Arctic Ocean or facing the wild temperature swings of a lunar crater.
That brings us to the real genius of this system, the aha moment in the AAE papers. They refer to it as functional dualism.
This is my favorite part.
It's so cool. The exact same physical coil of Litzwire acts as both the sensor to find the metal and the actuator to extract it. It has two completely distinct operational modes.
Let's walk through how this works in practice. Mode 1 is the sensing phase. The coil emits a very high frequency, relatively low power electromagnetic field. As the robot sweeps over an area, say, scanning the ocean floor, the coil is constantly reading the feedback from that field. It is looking for minute changes in electrical impedance and phase shifts.
How does a magnetic field detect what kind of metal is buried in the mud, though?
Because every element in the universe interacts with an electromagnetic field slightly differently. When the high-frequency field washes over a buried conductive object, that object subtly distorts the field.
Okay.
Gold creates a different distortion than platinum, which creates a different distortion than, say, a rusty tin can.
Right.
The coil senses these changes in impedance, essentially how much the object resists the field, and the phase shift, which is a tiny delay in the signal bouncing back. By analyzing those two factors, the system can literally feel the precise conductive signature of the anomaly hidden in the sediment.
So scanning, scanning, scanning. Then, the instant it recognizes the specific signature of something valuable, it seamlessly switches to mode 2, actuation.
Right.
It drops the sensing field entirely and fires a massive pulse power mode. The brief calls this a traveling magnetic field. What is a traveling magnetic field actually doing to the metal?
This field passes straight through the water and the mud, and it hits the target metal. Because the magnetic field is fluctuating, it induces what are called eddy currents inside the metal itself.
Eddy currents, like little whirlpools of electricity.
Exactly like whirlpools. The fluctuating magnetic field forces the loose electrons inside the gold or platinum to swirl around in tight little circles. Now, a fundamental rule of physics is that any moving electrical current generates its own magnetic field.
Oh.
Right. So these tiny whirlpools of electricity inside the metal create a secondary magnetic field that pushes back against the primary field coming from the robot.
So the robot creates a magnetic field, which forces the metal to create its own magnetic field, and then those two fields interact.
Yes. And the interaction between those two fields generates something called a Lorentz force. It creates an actual physical push or pull on the metal object, directing it along the phase velocity vector, basically the path defined by the coil. It is a physical force generated entirely out of invisible fields.
I was trying to wrap my head around this dual mode concept where the sensor and the extractor are the same piece of hardware. Tell me if this analogy holds up.
Let's hear it.
It is like a bat flying through the dark, using echolocation to hunt for a moth. The bat is sending out high-frequency sound waves, listening for the bounce to figure out where the moth is and what kind of insect it is. But in the case of this cyber actuator, the very nanosecond the sound wave hits the moth and confirms it's the right target, the sound wave itself instantly hardens into a tractor beam and physically yanks the moth right into the bat's mouth. The radar is the claw.
That is an exceptionally accurate way to visualize it. The radar is the claw. You do not need a camera to find the object and a separate robotic arm to reach out and grab it. It is the exact same hardware emitting both the detection wave and the extraction force.
That's just brilliant.
It really is, and this seamless integration leads to a second critical concept that Krimenov details in the documents. He calls it ontological selectivity.
Ontological selectivity. That sounds like a philosophy term, not an engineering one.
It does, but it describes a profound physical reality, and it is the ultimate solution to the environmental destruction problem we talked about earlier. Because the Lorentz force relies entirely on inducing those eddy currents, it only acts on materials that have high electrical conductivity.
Meaning what, exactly?
Meaning the surrounding environment is literally blind to the force.
Oh, because things like dirt and water don't conduct electricity the same way metals do?
Precisely. Basalt, quartz sand, deep-sea mud, glacial ice, the vacuum of space, none of these can sustain the necessary eddy currents. So when the coil fires that massive electromagnetic pulse, the force literally passes right through the useless dirt like a ghost.
Wow.
It only interacts with the conductive gold or rare earth nodule, grabs it, and pulls it out. The non-conductive mud doesn't even feel a breeze. It doesn't know anything happened.
That is staggering.
Yeah.
You are selectively extracting only the valuable resource. If you go back to the traditional dredging method, the ratio of extracted metal to disturbed earth is, what, millions to 1? With this, the ratio drops to practically 1 to 1. You only move the object you want.
It is a surgeon's scalpel compared to a dynamite blast.
Okay, the physics makes sense in a laboratory setting, but if we try to put this on a moving vehicle, it raises a massive technical hurdle. If I'm flying an autonomous underwater drone over the seabed at a few knots, and I'm using the exact same coil to sense the metal and then extract it, how does it switch between those modes fast enough?
It's a great question.
Because if it takes the system even half a second to switch from the high-frequency radar to the high-power tractor beam, the drone has already flown several feet past the target.
And this is exactly where the physical constraints of the coil meet the bleeding edge of the microelectronics revolution. To make this dual-mode functionality work on a moving platform, you need switching speeds that were basically science fiction a decade ago.
Right.
And the unsung hero making this possible is a semiconductor material called gallium nitride, or GaN.
Now, I know silicon is the foundation of all our standard computers and smartphones. Why can't we just use silicon chips to switch the power?
Silicon is wonderful for processing logic, but it is terrible at handling massive surges of high voltage power quickly. If you tried to use standard silicon transistors to instantly switch the kind of amperage required to generate a Lorentz force, the silicon would literally shatter or melt.
It just can't take the heat.
It can't handle the heat, and it can't handle the speed. Gallium nitride is a wide bandgap semiconductor. The chemical bonds in GaN are much stronger than in silicon, which means it can conduct electrons far more efficiently and handle vastly higher voltages without degrading.
So it's basically a much more robust pipe for the electricity to flow through.
It is a more robust pipe, and crucially, it is a pipe with a valve that can open and close at unimaginable speeds. GaN semiconductors allow the cyber actuator to switch power at the nanosecond level.
A nanosecond.
A nanosecond is 1/1000th of a second. To put that in perspective, a nanosecond is roughly the time it takes light to travel 1 foot.
That is almost impossible to conceptualize.
It happens faster than human thought. So the sequence works like this. The coil is humming along in its high-frequency sensing mode. It detects the specific phase shift of a gold nodule.
Okay.
In a few nanoseconds, the GaN transistors switch the circuit, shutting off the sensor and allowing a massive surge of power from the capacitors to flood the coil. The coil generates the Lorentz pulse, extracts the metal, and in a few more nanoseconds, the GaN switches the power back to the sensing circuit.
And the drone hasn't even moved a millimeter during the entire operation.
Exactly.
Okay, but generating a magnetic field strong enough to physically pull a piece of heavy metal out of compacted mud has to require an immense amount of electricity. The brief mentions that the actuator is highly energy efficient because it uses a high duty cycle. I need you to translate that because it sounds like a contradiction.
It does sound like one, doesn't it?
Yeah. How can firing massive power surges be energy efficient?
It all comes down to how long the power is actually on. Think of a high-powered strobe light at a concert. Every time that strobe flashes, it is blindingly bright. It requires a massive surge of energy to create that intense burst of photons.
Right.
But if you measure the total electricity that strobe light uses over the course of a minute, it is surprisingly low. Why? Because the light is actually turned off 99% of the time. The flashes are just incredibly short.
Ah, I see. So the I-DPCM actuator is acting like a strobe light for electromagnetism.
Exactly. It uses a high-duty cycle pulse. It delivers an extreme peak Lorentz force utilizing massive amperage, but it only sustains that pulse for a fraction of a millisecond, just long enough to physically yank the metal free of the sediment.
But because the pulse is so incredibly short, the average power consumption over time remains very low.
Yes.
And that is absolutely vital because these autonomous underwater vehicles and space drones run on batteries. You can't plug them into a wall.
Really?
If the coil drained the entire battery pack in 10 minutes, it would be commercially useless.
Precisely. The GaN switching, combined with the high-duty cycle, allows a battery-operated drone to perform thousands of high-power extractions on a single charge.
Okay, so we have the super fast GaN switches acting as the muscles, and we have the energy-efficient power delivery. But who is driving? Who is making the decision to pull the trigger on that pulse? It clearly can't be a human sitting with a joystick up on a surface ship. I mean, human reaction time is about a quarter of a second, which is practically an eternity at these speeds.
It is completely autonomous. The brain of the cyber actuator is an onboard piece of hardware called an FPGA, a field programmable gate array.
This is where I get a bit lost in the computer science. I know CPUs are the brains of our laptops, and GPUs handle graphics and are used to train large AI models.
Right.
Why does this system require an FPGA instead of a standard computer processor?
It has to do with how the hardware actually processes information. A standard CPU, even the fastest one in the world, operates sequentially. It is a von Neumann architecture.
Meaning step by step?
Right. It takes a piece of data, reads the instructions from the memory, performs the calculation, and writes the answer back to the memory.
It's like a really fast, short-order cook reading tickets. They can cook very quickly, but they still have to read the ticket, find the ingredients, cook the meal, and ring the bell one at a time.
That's a great analogy. And because of those steps, a CPU always has a tiny bit of built-in latency, a few milliseconds of delay. In standard computing, you never notice it.
Sure.
But when you are flying a drone over the seabed trying to catch a target in a billionth of a second, that latency means you miss the target. An FPGA is entirely different. It does not have fixed instructions waiting in memory. It is essentially a massive grid of raw, unassigned logic gates.
Unsigned?
Yes. You literally program the hardware itself. You wire the physical pathways of the chip to perform one specific algorithm.
So to follow the kitchen analogy, instead of having a cook read a ticket, you literally physically rearrange the entire kitchen. You build a custom slide from the fridge, through the oven, directly onto the plate, so the food basically cooks itself instantly on the way out the door.
That is brilliantly put. You are hardwiring the algorithm into the silicon. Because the data flows directly through the physical logic gates without having to stop and consult a memory bank, the FPGA can run real-time artificial intelligence with virtually zero latency. It is instantaneous.
So let's look at the complete decision loop of this machine, because putting it all together is mind-bending.
Let's do it.
The coil is sweeping over the mud, acting as a radar. The FPGA instantly receives the impedance data. The hardwired AI analyzes that signature and classifies it. It looks at the wave and says, that is not background noise, that is not a piece of trash, that precise signature is a neodymium nodule.
Right.
The AI then calculates the exact adaptive parameters needed for the pulse, how much power, what frequency. The GaN transistors receive the command and switch the power. The coil fires the Lorentz force. The metal flies up out of the mud and into the robot's collection hopper.
And it doesn't stop there.
All right. The sensor then pings the ground again to verify the metal is gone, logs the geological data, and uses that interaction to update its learning model for the next scan.
And all of that, the sensing, the AI decision, the high power extraction, and the verification, happens in a fraction of a second.
It is almost biological. It feels less like a machine processing code and more like a reflex.
That is the perfect word for it. When you accidentally touch a hot stove, your brain doesn't have to consciously think, my hand is experiencing extreme heat, I should send a signal to my muscles to retract my arm. Your nervous system handles it autonomously at the spinal level before you even feel the pain.
Right, it's automatic.
It is a closed reflex loop. And this brings us to the categorical shift in robotics that the TPAE brief is proposing.
The idea of the cyber actuator itself.
Historically, robotics has been highly modular. You have a camera module acting as the eyes, you have a central computer acting as the brain, and you have a mechanical arm acting as the hand. They are separate systems talking to each other over a network.
Which introduces latency.
Exactly. Krimenov is introducing something fundamentally new. The cyber actuator is an indivisible pairing of edge, artificial intelligence, and a programmable electromagnetic field operating in a closed nanosecond loop. You literally cannot separate the sensor from the AI or from the actuator. They function together as a single intelligent organ.
Wow.
It is giving robots a localized, intelligent nervous system for interacting directly with matter.
This is why the strategic brief feels so urgent. They aren't just trying to sell a cool new tool to bolt onto an existing submarine. They're trying to define an entirely new standard for how machines are supposed to operate autonomously in the wild.
They are rewriting the foundational rulebook of robotics.
So, we have explored this incredible theoretical framework. We have broken down the Litzwire physics, the Tian'an microchips, the FPGA brain.
Yeah.
But a technology this radical doesn't just leap straight from a whiteboard onto an asteroid. How do we actually deploy this tomorrow? Where is the immediate proving ground?
Well, the strategic brief makes it very clear that the fastest route to commercialization, and frankly the most lucrative immediate market, isn't cleaning up space debris.
No.
No. It is right here on Earth, in the deep ocean and the Arctic shelf.
The subsea domain.
It's the perfect crucible for this technology. And to appreciate the impact, we have to deeply contrast this with the legacy methods currently being debated by mining consortiums. Let's say a major corporation wants to harvest those polymetallic nodules from the Clarion-Clipperton Zone in the Pacific. We touched on this earlier, but the logistics of the old way are staggering.
It involves massive maritime infrastructure.
Right. It involves deploying an enormous surface vessel, essentially a specialized drill ship, which costs hundreds of thousands of dollars every single day just to keep on station. From that ship, they lower a rigid vertical riser pipe miles down through the water column to the abyssal plain.
Just a giant pipe.
A giant, incredibly heavy pipe. At the bottom of that pipe is a harvester machine the size of a house. It crawls along the delicate seabed, crushing everything under its treads. It uses massive hydraulic pumps to suck up everything in front of it. Mud, rocks, nodules, biological life.
And they pump all of that raw, undifferentiated mass miles up the pipe to the surface ship. They run it through sorting screens on the deck to pick out the few nodules they actually want. This is the part that truly boggles the mind. They take millions of tons of that dead processed mud and pump it right back into the ocean,
creating those massive, toxic, suffocating plumes we discussed.
It is spectacularly inefficient from an energy standpoint, and it is ecologically disastrous.
Now, replace that entire chaotic operation with the I-DPCM paradigm. You no longer need a massive surface ship bobbing in the waves. You deploy an AUV, an autonomous underwater vehicle. It looks like a sleek torpedo or a small submarine.
Okay.
It swings down to the seabed and hovers about a meter above the bottom, remaining completely silent and entirely neutrally buoyant. It never actually touches the ground.
It just glides over the mud.
It glides. It uses the high-frequency coil to sense the gold or the rare earth nodules buried in the sediment. The FPGA recognizes the target, the GAN switches fire, and the Lorentz pulse is generated. The valuable metal simply pops out of the silt, pushed by the magnetic force, and floats up into the drone's belly.
And the ground below.
The non-conductive mud beneath it never moves. The deep-sea worms and sponges living next to the nodule are completely undisturbed.
I have to admit, when I was reading through this section of the brief, there's a very specific semantic nuance that stood out to me.
Oh, what was that?
The author, Krimenov, explicitly states that I-DPCM is not a zero-impact technology. They are very careful to avoid using that kind of corporate greenwashing terminology. Instead, they define it as a selective interaction-first technology. What is the distinction there, and why does it matter?
That is a crucial nuance, particularly for anyone dealing with international regulatory bodies like the ISA. Scientifically speaking, zero impact is a myth. It does not exist.
Right.
Anytime human industry enters an untouched ecosystem, you have an impact. If you use a magnetic force to remove a metal nodule that a deep-sea sponge happened to be growing on, you have impacted that sponge. You have altered the environment.
Because you can't remove matter without changing the state of the area.
But environmental regulators are not looking for absolute zero impact. They know that is impossible if we want any resources at all. They're looking for acceptable, traceable, and minimal ecological footprints.
Oh, I see.
Selective interaction first means that the machine is programmed to make an active, AI-driven choice to only take the specific target material, leaving the surrounding geology and biology as close to undisturbed as physically permitted by the laws of physics.
And the Breeze mentions that the FPGA logs every single decision. It provides what they call traceable intervention data.
That is the regulatory goldmine. The robot can literally generate a cryptographic log that says, and this exact GPS coordinate, I sensed anomaly X. I calculated that it required Y amount of Lorentz force. I fired the pulse, extracted the nodule, and here is the secondary scan proving that the seabed around the extraction site remains physically intact.
You can hand that data directly to an environmental auditor.
Exactly.
That level of accountability is unheard of in heavy industry. And the operational implications of severing ties with surface ships are huge. Because you aren't forced to pump millions of tons of mud up a vertical pipe to a ship, you don't need the ship at all, which means you can deploy these machines in places where surface ships simply cannot operate.
The Arctic shelf.
Exactly. The brief heavily focuses on mining under the multi-year Arctic ice.
Because the Arctic holds some of the most critical unexploited reserves of rare earth elements, which are vital for national security. But the surface is covered in thick, shifting sea ice. A traditional drill ship would be crushed.
But with I-DPCM,
you can deploy a fleet of autonomous AUVs from a military submarine beneath the ice or from a specialized coastal base. The drones swim hundreds of miles under the ice cap, silently harvest the necessary rare earths from the seabed, and swim back to the base to unload, all without a single surface vessel ever having to brave the ice flows.
And they don't do this as lone wolves.
All right.
The brief explicitly envisions a swarm architecture.
Swarm robotics is the key to scaling this to a planetary level. You don't put all your capital into building one giant billion-dollar mega machine that represents a single point of failure.
Because if it breaks, you're done.
Right. Instead, you build thousands of smaller, relatively cheap AUVs, each equipped with an I-DPCM cyber actuator. They communicate with each other acoustically through the water, forming a dynamic, self-organizing network coordinated by a higher-level swarm AI.
So let's say you have a swarm of 300 drones mining under the Arctic ice. If one drone suffers a catastrophic battery failure or gets crushed by shifting ice, it doesn't matter. The swarm intelligence just reroutes the remaining drones to cover the lost drone sector, and the mission continues uninterrupted.
It introduces total system redundancy. And more importantly, it completely democratizes ocean operations. You no longer need the massive centralized maritime infrastructure of a multinational oil company to operate in the deep sea.
That is a total paradigm shift for oceanography. But as we established early on, if a technology relies purely on electromagnetism and artificial intelligence, the physics don't care about the environment. Electromagnetism works underwater, but it works exactly the same in a complete vacuum.
Which transitions us beautifully from the crushing depths of the ocean to the absolute void of space.
Let's take this physics up to the stars. Let's revisit the Kessler syndrome and cleaning up low Earth orbit.
We discussed earlier that trying to catch hypervelocity space debris with a physical net is mathematically impossible because you have to burn massive amounts of fuel to match speeds. But with I-DPCM, the paradigm completely shifts to what they call orbital remediation.
Sweeping space rather than catching it.
Exactly. Imagine deploying a swarm of small solar-powered satellites equipped with these cyber actuators. They fly in a wide, sweeping formation through a debris-heavy orbital lane. They don't try to chase down individual bolts, they just hold their orbit. They use the high-frequency sensing mode to detect a metallic fragment flying toward them. When the debris enters the effective range, the FPGA calculates its trajectory and fires a precisely calculated Lorentz force pulse.
But they aren't trying to pull the debris into a cargo bay, right? They use the magnetic force to push against it.
Yes. They induce the eddy current in the aluminum or steel debris, and they push. They use the electromagnetic field as an invisible bumper. Now, you don't need to completely stop a piece of debris moving at 17,000 miles an hour.
Right, that would be impossible.
Even a tiny electromagnetic shove alters the debris's orbital velocity. If you slow it down just a fraction of a percent, its orbit naturally decays. Gravity takes over, and the debris falls into the Earth's upper atmosphere where it safely burns up upon re-entry.
That is brilliant. You are using the kinetic energy of the debris against itself. And because the satellite uses solar panels to charge its capacitors, it doesn't need to carry massive tanks of chemical propellant. It can deorbit thousands of metallic fragments at a distance without ever physically touching them, using only renewable solar energy converted into electromagnetism.
It makes planetary-scale debris removal mathematically viable. And once space is safe to travel through again, we can look at ISRU lunar and asteroid mining.
We talked about the asteroid Psyche earlier, which is theoretically made almost entirely of iron, nickel, and valuable precious metals. We also established that mechanical drills break in the abrasive regolith, and there is zero gravity to hold a bulldozer down. How does the cyber actuator solve asteroid mining?
The solution is elegant in its simplicity. You send a hovering space drone over the asteroid, it doesn't land. It never touches the abrasive dust.
It just floats.
It uses thrusters to hover a few feet above the surface. It scans the ground for the highest concentration of platinum or palladium. When it finds it, it fires the Lorentz force. The force ignores the non-conductive rock and regolith, grabs the conductive metal, and pulls it directly out of the asteroid's surface, floating it up through the vacuum into the drone's collection hopper.
It completely bypasses the need for gravity, traction, and mechanical wear and tear.
Kriminov refers to this ultimate vision as an amphibious technological core. The beauty of this invention is its universality. The exact same I-DPCM module, the identical physical Litzwire coil, nanocrystalline core, and FPGA brain can be fitted to an autonomous submarine in the Marianas Trench, a lunar rover in the Shackleton crater, or a terrestrial drone surveying for gold in the Australian outback.
Because the physics of electromagnetism is a universal language.
Exactly.
Okay, this is all deeply fundamentally fascinating science. But the documents we are reading today aren't just academic white papers published in a journal. They're highly calculated strategic business briefs. This is an active commercial maneuver happening right now in the real world. I want to shift our focus to the business intelligence aspect of the EPAE documents. What is the actual play here?
This is where we examine the race for validation and the construction of what corporate strategists call an IP moat. EPAE is executing a very specific, highly disciplined maneuver. They're offering a limited strategic notification to a select group of robotics leaders and defense contractors.
And they're very explicit in the text, right? They are not looking for a buyer right now. They're not trying to sell the patent to the highest bidder and walk away.
No, not at all. They are looking for a qualified industrial partner to establish a joint framework.
Right. And they have laid out a rigorous, step-by-step roadmap for validation. Step 1 is executing a mutual non-disclosure agreement. Step 2 is a confidential technical review, where the partner's engineers get to actually look at the underlying physics math and the AI algorithms.
And if that passes, they move to a feasibility study.
Then they want to build a controlled saltwater tank demonstrator, essentially proving the extraction works in a laboratory environment with real ocean sediment and pressurized water. From there, they integrate the coil into an existing ROV prototype. And finally, they conduct a full-scale deep-sea validation in the open ocean.
It is a very measured scientific approach to commercialization, but underneath that cooperative roadmap, there is a very clear stick they are holding, a threat.
The brief talks extensively about their IP moat.
In technology business strategy, an IP moat is your defensive wall. It is how you prevent massive corporations from just stealing your idea and outspending you. EPAE has already confirmed absolute global novelty in the European Union patent jurisdiction, with a priority date starting in 2025.
Meaning what exactly?
Meaning that the Patent Office has confirmed that absolutely no one else in the world has patented this specific functional pairing of edge AI and high-frequency electromagnetic actuation. They own the foundational intellectual property for this entire category of machine.
And the brief actually weaponizes this fact. It includes a direct warning to these robotics companies. It basically says, the immediate strategic risk to your company is not that I-DPCM is a fully industrialized, off-the-shelf product today. The risk is that your direct competitor becomes our first partner.
That is the crux of the entire business strategy. In any nascent disruptive industry, the first mover gains an almost insurmountable advantage. The first partner to validate this technology in the ocean gets to dictate the operational data. They get to define the engineering terminology for the rest of the world. Crucially, they get to sit down with regulatory bodies like the ISA and help write the global environmental standards based on their own proprietary machine.
If your competitor validates this first and sets the standard, they lock you out of the next functional generation of robotics. You will be stuck trying to sell environmentally destructive mechanical claws to governments that have already mandated clean electromagnetic cyber actuators.
It is an existential threat to legacy robotics manufacturers. But the brief also points out the massive upside. It is not just the robotics companies that benefit. By validating this technology, the partner opens up a massive, high-margin secondary market. Think about the component manufacturers we discussed earlier.
The semiconductor foundries making the GaN transistors and the FPGA chips.
Exactly. Right now, those chips are mostly used in terrestrial communications, data centers, and consumer electronics. I-DPCM creates an entirely new, incredibly lucrative use case for high-power, wide-bandgap semiconductors and peripheral edge AI chips.
Chips that must be designed to operate flawlessly in extreme environments.
Right, the freezing high-pressure abyss of the ocean and the irradiated vacuum of deep space. It is a market maker for the entire advanced microelectronics supply chain.
It is a fascinating blend of pure physics and cutthroat corporate strategy. Let's try to bring this all together and look at the whole tapestry we've unrolled today. We started this journey looking at a massive planetary scale problem.
Human civilization's desperate, growing need for critical raw metals to build a sustainable future.
Colliding head-on with the catastrophic environmental failure of traditional mechanical digging.
We explored how mechanical forces destroy the delicate ecology of the ocean floor, how they fail completely to address the hypervelocity threat of space debris, and how they physically break down in the abrasive, zero-gravity environments of other planets.
And the solution proposed by Alexander Kriminov and the Tri-AE team is a fundamental physics-bending shift in how machines touch the world. The I-DPCM cyber actuator. It abandons mechanical force entirely.
It uses the exact same list-wire coil and nanocrystalline core to act as both the high-frequency sensor to find the metal and the high-power magnetic tractor beam to extract it in a nanosecond, all driven autonomously by a zero-latency edge AI brain.
It creates a new reality where we can selectively interact only with the specific matter we want, leaving the environment around it completely physically untouched.
So after all this dense physics and geopolitical strategy, why does this classified level engineering matter to you, the person listening right now?
Yeah, why should they care?
It matters because the screen you are reading this on, the battery in your electric car, the advanced medical devices in your local hospital, and the entire future of human space exploration depend completely on our ability to acquire these conductive materials. We are currently heading toward a severe resource bottleneck that could stall human progress and permanently damage our planet.
And I-DPCM represents a bridge over that looming collapse.
It provides a technological pathway for us to interact with our universe, to take exactly what we need to survive and thrive without destroying the very environments we are desperately trying to protect.
It really is a profound shift in how we view our relationship with the physical world, which brings me back to that vast, sweeping desert we were standing in at the very beginning of the show. You're standing there, the sand beneath your feet is perfectly still, not a grain is out of place, and the pure gold is just vibrating, lifting out of the earth and flying into your hands.
It's quite an image.
It leaves me with this lingering thought. If we successfully scale this, if we deploy these swarms of AI-driven, invisible electromagnetic fields that can selectively pull specific elements right out of the earth, out of the deep oceans, and out of passing asteroids, at what point does human mining stop looking like a heavy, destructive industry and start looking like digital alchemy? Keep wondering, and we'll see you on the next Deep Dive.